Well, greetings everybody. Here is a problem from our assignment that I think is a really good problem for me to do because it touches on so many things that have come up in our class recently. What we have here is this new topic of conditional and absolute convergence, but as part of answering that, figuring that part out, we have to know what are alternating series and how do you analyze them. We'll use something called the limit comparison test along the way. And there's some other things that come up too that I think would be good to touch on. Okay, so that's why I want to do this one. Now, the basic question here is, does this series converge absolutely or conditionally, or does it just diverge? So let's talk about what that means. So I have a little flowchart here about what absolute and conditional convergence mean. Okay, so let's say that we start with some series that we know converges. Wait a second. What if we don't start here? What if we start with a series that diverges? Well, then of these three options, does it converge absolutely? Does it converge conditionally? Or does it diverge? Well, if it diverges, in its given form, then it diverges, okay? But let's say then that we start with some series that we know converges. All right. Now, does the same series with all positive terms also converge? That's the next question. So I start with some series that I know converges. And then my next question is to ask, if I take that series and make all the terms positive, would it also converge? That's what this absolute value means. So AN, that's the formula that would give you the terms of the original series. If I put an absolute value on that, all it does is make all the terms positive. So if this original series has some negative terms, this corrects all that to be positive terms. Doesn't change the numbers, just makes all the terms positive. So does this series also converge? If that's yes, then we say the original series converges absolutely. If the answer to this question is no, then we say the original series converges conditionally. Okay, so that's how we make our decision. Now, let's answer that for this. So I guess my first question with that series that I'm given, which you see right here, is, well, does that series converge or diverge? Okay, because remember our flowchart says, well, we have some series that converges, and then from there we'll decide if it converges absolutely or conditionally. So what I notice about this series is that it's an alternating series. That -1 to the power k plus 1, that'll give me alternate positive and negative signs. And otherwise, like this k plus 2 over k squared minus 1, that's always going to be a positive number. So I know the product here is going to give me alternating positive and negative terms, okay? Now, how do you know if an alternating series converges? Two things have to happen for it to converge. An alternating series will converge if the absolute value of any term is more than the absolute value of the term that comes right after that. Now, I'm not going to prove that at the moment, but let's say if you looked at this series, if you looked at it term by term, you'd see that that's true. That's not proof, but for now, let's say, okay, fine. Yes, it satisfies this first condition. The terms of this series in absolute value get successively smaller, so check on the first one. But also, the limit to infinity for the absolute value of this expression, where, well, how would you get the absolute value of this original expression? Well, the only thing that could possibly be negative in this formula is that -1 to the k plus 1 power. So the absolute value of this original expression is just k plus 2 over k squared minus 1. And I meant to write there, I didn't write it, but I'll do that right now. If that is 0, that's not as nice as I'd like it, but that second condition is that this limit is 0, and it is, okay? The limit of that k plus 2 over k squared minus 1 as k goes to infinity is 0. Now, alternating series will converge if both of these things happen, and they both do. Okay, so that's where we start. This is a convergent series, okay, by the alternating series test right there. Okay, so here we are on the flowchart. I have a series that converges. Now I need to look at the same series with all positive terms. Okay, so let's look at this. I guess technically that would be this. If I took absolute value and put it on that formula that defines that original series. Now that's kind of an awkward thing to deal with because there's a lot of extra symbols there I don't need. How would you just take the absolute value of this? Well, I alluded to that over here. The only component of this formula that could possibly be negative is that negative 1 to the power k plus 1. So if you want to just briefly calculate the absolute value of this, you could just drop that, and it's going to leave you with k plus 2 over k squared minus 1. Now from here, I noticed that in this question, it alludes to a few tactics you can take, and one of them is the limit comparison test, okay? So what will work is using the limit comparison test on that with the series 1 over k. All right, and I'll show you why that works. Now, the limit comparison test involves having two series, one that we have to make a decision about, and that one we're comparing with that we already know how it works. And we find this limit here, the limit to infinity of the one over the other, okay? And we see what that limit is. We'll get a number, and then we look at these three cases for the test to decide what our answer is. So I'm going to compare this series with that one using the limit comparison test. Now, here's that limit that it says we should evaluate in the limit comparison test. Okay? I start here. I do a little algebra and I get there. This is an indeterminate form. If k goes to infinity, then the top and bottom of this go to infinity. Okay, so indeterminate forms like that can be evaluated by L'Hopital's rule. L'Hopital's rule says when we have an indeterminate form like this, find the derivative of the top and bottom individually and reevaluate. If I do that once, I still get an indeterminate form. If I do that twice, I get 1. Okay, so the limit here in the limit comparison test is 1. That's what that number is. Okay, now what does that mean? Which case does that put us in? Does it put us in case 3? Well, we didn't get infinity, so no. Does it put us in case 2? We didn't get 0, so no. Does it put us in case 1? Well, I got a limit of 1. Okay, that's a finite positive number. And it says the series I'm deciding about and the one I compare with either both converge or both diverge. They do the same thing as each other. So what does this one do? I'm trying to decide about that one. But in order to do that, I have to know what this one does. So what does this one do? Well, that series diverges. It's a type of p-series that diverges. So we say, so does this one. Okay, so does this one. This series right here diverges. Now, what did we figure out? Here's what we figured out. I started with a series that I found converged by the alternating series test. Okay, then when I looked at that same series with only positive terms, I found that it didn't converge. So no to that. And so that means what? The original series converges conditionally. So what we say about this is the series converges conditionally. Along the way, we use the alternating series test and the limit comparison test to show that. Okay, so that's how it works. All right. Like I said, I use several things that we've seen in the class up till now. Any one of which you could have all these questions about, but the video will be too long to go into tremendous detail on any one part. One thing, though, that I should go into a little more detail about is this part of the alternating series test. Here I just said, well, if any term is bigger than the one that comes after it in absolute value, then that's part of the alternating series test. Okay, but I didn't prove that. I mean, I was just saying, like, well, maybe you would look at the terms and be satisfied that that's true. But that's not proof, and that's not really how we do math. So I should show you how you would prove that in case you needed to. In this problem, it doesn't say that we have to do that. So I guess if you were comfortable with this first part, then that would be okay. So here's how we show that. Now, here's this alternating series that we started with. And if you write some of the terms out, you can tell that they get smaller and smaller and smaller. You know, any one of these terms in absolute value is bigger than the one that comes after it. Okay, but that doesn't prove it, right? So how do we prove that? The way that we prove it is look at the absolute value of this, which is k plus 2 over k squared minus 1. Find its derivative and show that the derivative is negative. If the derivative were negative, it means that that original function was decreasing, and that means that it's getting smaller. If any number is more than the one that came after it. So if I find the derivative of that by the quotient rule, I get this. Now, how can we decide that that's negative? Well, okay, so one way to do it without graphing it or something like that would be like this. I could make a sign chart for that quadratic part at the top. I could figure out that it's 0 at negative 3.7 and negative 0.3 with a little rounding. Using test values, I could figure out it's negative, positive, negative. And then from there, I could say, well, this expression, which is the derivative, the top will be negative for all positive numbers, you know, right of negative 0.3. And that bottom part, because it's a square, will always be positive. So, you know, as far as a proof goes, that would prove that the derivative is negative and that this is actually decreasing, okay? Another way that you could do it is, what if I took this derivative and I graphed it and I could see that it was negative? Like my prediction here is it's negative once you get past or to the right of 0.3, okay? So, well, let's see. I could go to something like this, a grapher of some kind, and I could put that formula in, and you know, here's the x-axis, here's the y-axis. I see it dips below the x-axis and becomes negative past this point. What's that point? Negative 0.26. Okay, that rounds to 0.3. That's consistent with the way I solved it. Okay, so I need to show you that. And even as I did, I left some of the details out. There's some algebra for working with this, solving quadratics, making the sign chart. So just keep in mind, with any video that I can make, by the time you get to calculus 2, it's, you know, all the work's going to depend on lots of things that came before it. Now, if you're happy with the detail in the video, then that's great. That's what I would hope for. But it might be that you're unsure about how some of the limits are done, that you're unsure about some of the theorems and concepts that have come up before it, such as the limit comparison test, or it might even be just algebra. Okay? If that's the case, let me know.